Okay, ladies and gentlemen, I think it's time to start this session. It's about research on processor architecture design and deployment. And my name is Jari Nurmi. I'm a professor in Tampere University, and today we are going to hear 3 researchers from our university who were picked to this session, and all of their work is somehow related to processor architectures or processing architectures of different kinds. But let's move on. So we can start from the first speaker. So Esko Pekkarinen, I will give the floor to you. Go ahead.
Thank you. Good afternoon, ladies and gentlemen. It is my pleasure to present some of our recent research work from the System on Chip research group in Tampere University. And my topic today is modeling RISC-V architecture in Cactus 2. So shortly about the speaker. So my name is Esko Pekkarinen. I am a doctoral researcher at the Tampere University. My topics and interests are in design tools and specifically in IP-XACT based design. I also have some teaching on courses such as system design and real-time systems. And I've been part of the Cactus 2 IP-XACT design team since 2013. My previous research work is related but somewhat different. So for my master's thesis, I worked on simulations on wireless sensor networks. And for my bachelor, I did modeling on applications on multiprocessor system on chip platforms. But the motivation for today's work comes actually from, I would say, the last 5 years, we have seen a very strong momentum gain for RISC-V. And this is not only on the research side, but also on the industrial side. So we are seeing news like Samsung taking up RISC-V cores for their applications. This is from last December. And another interesting news from Western Digital, also from December, is that they are announcing 2 new cores. And what is more interesting there is they are also providing the RTL level design open source. So the RISC-V is a standardized instruction set architecture, which has optional and custom extensions. So not every RISC-V core is identical. You can pick what extensions you need for your applications, and you can also design your own extensions. But also this means that all the implementations are different, and there's a lot of different implementations. We already know that in modern embedded system design, the complexity of the systems is so huge that a high abstraction level is mandatory if we want to cope with the large scale designs. And some of the features we have seen are IPs must be reused efficiently. There are multiple configurations. So for example, the same RISC-V core could be used for very low power applications on very low power platforms, but also on the high performance side and anything in between. So we need a lot of different configuration options. And finally, automation is mandatory. Yet from our experience, modeling, which gives this high level of abstraction, is seen as very tedious if we compare it to a traditional hardware description language driven design, if we ask the designers. And our interest in this topic was, all right, what are the features that make it so? And can we help mitigate those problems and promote modeling and design automation also in not only RISC-V, but in embedded systems in general? And what we found out is that some of the features, and one of the biggest issues there is that legacy code bases are very difficult to adapt to the modeling patterns and the modeling environments that could be used. And also, the benefits of modeling only become clear after a longer time period. So if we look at the design challenges in this more traditional hardware description language driven model or design flow, I've divided it here for two levels. So on the design level, on the module and the lower level, we found out that the HDLs mix three aspects of the design. So there's behavior, there's structure, and there's control for configuration. And the same language and the same tools are used for all of this. We have implicit references that are evaluated late in the design flow. And this works perfectly fine for a small project, but we found ourselves with more trouble as the project grows larger and larger. So for example, if we have tens of thousands or hundreds of thousands of files, we have multiple vendors, we have different teams working on different parts of the system. This becomes really hard to maintain. And another problem there is that we very quickly may find ourselves having naming conflicts, and we're dependent on different tool or file versions. And what we found out is agreeing on coding style and means of working doesn't seem to help. And on the system level, we get even bigger problems because we must use that higher abstraction level. So there's more tools, there's more languages, and we use a lot of different specification styles. So we have different formats, different meanings, and different intention when we're using these tools and languages. We often compromise the clean design for reuse because we have to hit a certain deadline. And integration from different vendors is difficult if we don't agree on how the IPs communicate with each other. And in general, the scale is so large that nobody can comprehend the whole system in detail at once. And this is where we found out standardization helps. And the IEEE IP-XACT standard is one of the most promising ones. So it's a standardized XML format for IP block models, which in IP-XACT terms are called components. They can have file references to files where the behavior is defined. We have a SOC design model where we instantiate these components to create hierarchical designs. And then we have means of configuration. Finally, there's a set tool interface to make sure the data can be accessed in a uniform way. And this has become the de facto standard in the industry. The benefits there are its vendor implementation language and tool independent. And the value promise is that we get easy reuse of IPs, which leads to better productivity. Now, Cactus 2 is an open source IP-XACT based toolset designed for embedded system design and developed at the Tampere University. So if we take the IP-XACT, what it offers as the base, what more can the tool provide? So first of all, we need means of importing these HDLs into IP-XACT as easy, as efficiently as possible. We already have the design information in the IP-XACT, so we can use generators to generate the structural description. And these together can be fed to the simulation and synthesis design flow and the tools there. What is more, in the IP-XACT description, we may have addressing information. So this can help our software development. And also, there's a lot of metadata stored in the IP-XACT. So we can use this to generate, for example, the documentation. And we recently got an email from one of the users who said that they use the tool for generating the top-level connectivity with thousands of wires. And normally this is done manually, and it's a lot of repetitive work for the designer. So Cactus was first released in 2011, so 9 years ago. And in that time, we've seen a lot of different tools come and go, but Cactus 2 has remained relevant. And we think this is due to 3 different factors. We have stayed true to the standard. And when the standard was updated, we also were very quick to adopt the 2014 standard. We have a graphical user interface. The first Cactus 2 version was more like a graphical editor for the IP-XACT XML. But we have come a long way from there, but we've kept this graphical because it helps on the top level to understand what the system is all about. And finally, we have tried to make the tool as usable as possible. So our modeling target recently has been the PULPino RISC-V microcontroller, and the top level is shown here. And this is published open source. It has 250 files and almost 70,000 lines of, well, mostly system Verilog. And it comes in 21 different repositories, so assembling it together is an effort in itself. And for the core, there are 4 different configurations. So first, we have the RISC-V configuration, where we have the RV32 ICM instruction set, which is the integer and the multiplication. And then there are some custom PULP extensions. The second configuration is if we take the floating point support there as well. The actual core is depicted here. So you can see it's a 4-stage pipeline. And some of the extensions are also visible here. For example, the product unit isn't part of the standard extensions. The other two configurations are zero risky, which is 2-stage pipeline. So it leaves the extensions out and there's no support for the floating points. And then there's the smallest micro risky, which then even takes the 32 general purpose registers down to 16. And the effort we've done here is modeling this in IP-XACT. So we took the component interface from the source file using the Cactus2 import. We get the ports and the parameters. The behavior is still in the original source files, and they are referred from the component. The submodule instantiations and connectivity currently has to be done manually. So on the top level in the Cactus2 tool, this is the view we get. So we have the different submodules and their connectivity. The signaling and ports are grouped to buses and bus interfaces. And then we gathered these 4 configurations into what's called component views. So selecting a view selects you one of those 4 configurations for the core. And this whole model is available in GitHub. Currently, it's closing on 200 IP-XACT files and almost 100,000 lines of XML. But what I'd like to share today with you, most importantly, is what are the challenges and what we learned from this modeling effort. So one of the 4 cases where this traditional HDL and IP-XACT really have difficulty in capturing the details is conditional structure. So configuration values are used to enable or disable part of the structure. So for example, module instantiations, wires, ports. And an example is given here. So we are changing depending on the value of this define, the module instantiation that we want to have in the structure. And this is a very powerful and flexible mechanism in the HDL. Unfortunately, IP-XACT is inherently very static in the structure. So this is somewhat difficult to capture. But what we can do with the 2014 standard is most of the elements have this isPresent attribute, which functions such that if the value is false, it is as if it doesn't exist. So we can enable part of the structure. However, the pitfall there is that not every element has this attribute. And in cases like this, I would actually consider creating another design and then you switch between those designs depending on what is your intent. So what parameter value you have there. Another problematic structure is generate loops. So where we want to create regular structure, such as module instantiations or wire connections. An example is given on the right. And in IP-XACT, we just have to replace these with static instances. And an observation is that usually these generate loops and the conditional structures we had on the previous slide, there is a very limited set of reasonable options. So there's no need to create every possible combination. The third pitfall we found out is coupling structure and behavior. So it's very typical to see that we use glue logic to make some simple manipulation of data as part of the structural description. And these are typically things like multiplexing or simple and or not. Another example is given here. So for example, here we see there's an AND operation, and then here we do some multiplexing to select if we take the data read from the boot ROM or the RAM memory. However, in IP-XACT, all behavior must be contained within components. There's no behavior in designs. So what this in practice means, we have to move all this glue logic to new components. However, it must be said, this is impractical if we are doing basic ANDs or such. And finally, we have configurable interfaces. For example, if we want to use modules where we can set the interface number according to a parameter. An example is given here. Again, in IP-XACT, the interfaces are static, so we have two options. We can define the maximum set and leave any unused unconnected, and then trust that our synthesis tool leaves out any unused wires. Or then we use the isPresent to check the limits so that proper amount of interfaces is present. Another option is to automatically generate components with the correct number of bus interfaces using a template. So currently we have moved away from PULPino, and we are working on exploring how we can use modeling in a system level project. So not only this microcontroller, but taking the next step where we have different subsystems interacting. And the target here is code generation for system on chip level. We have moved from PULPino to this PULPissimo microcontroller. They are very similar in many aspects, but the interesting difference is that with PULPissimo, we get a micro DMA, which allows better CPU utilization. In PULPino, every transfer between the peripherals must be done by the CPU. And then there are other more interesting peripherals such as SDI. So to conclude, modeling benefits from good practices in the code and project organization. So having clear and well-defined interfaces, decoupling structure and behavior, and it should be without saying one module per source file. IP-XACT cannot capture all the features in HDLs, but we can work with this and mitigate the effort there. And modeling work targets for improved understandability through higher abstraction, reusability by standardization, and through these to improve productivity. Thank you.
Okay, thank you, Esko. We have probably time for one or two questions, and there is one non-technical question in the chat. So there's a question if screenshots of the slides can be posted on Twitter.
Yes, that is fine for me.
Okay, I can ask the same from Joonas and Hesam too. Is it okay if some of your slides will appear in HiPEAC's Twitter?
Yes, it's okay.
Yes, for me too, it's okay.
Okay, that question was answered. I can ask one question on this Cactus 2 user base. So what kind of customers you have for the tool, and how many customers, if you can keep track on that?
So I cannot disclose the names of the customers we have and the people we are in contact, but I would say there are some mid-sized companies and even some very large companies.
Okay.
The numbers are really difficult to tell because the way we keep track is through the downloads from GitHub.
Yeah, so you don't have any specific licensing agreement to be signed to get it, so it's fully free to download by anybody.
It's free to download and free to use.
Okay. All right. There are no more questions, so thank you, Esko, and we move forward.
Thank you.
Then we have Joonas Multanen next, so if you take the stage for yourself and go ahead.
Okay, thank you. Let me share my screen. There.
Okay.
So, is it okay?
Yes, that's perfectly okay.
Good. So I'm Joonas Multanen. I'm also a doctoral researcher at the Tampere University, and I'm a member of the Customized Parallel Computing Group. And my topic for today is low power, high performance ASIP design with open source tools. So basically, I will first have a brief introduction to a processor architecture called transport triggered architecture, because it is needed in the second part, where I'm presenting our toolset, which is able to produce and compile and simulate these TTA architecture processors, and which are also open source and free to download, by the way. And lastly, I'll show 2 case studies using our tools. So first, this brief introduction to TTAs. So basically, the main thing in TTAs is that the internal data paths are exposed in the instruction set. So what that basically means is that contrary to the operation triggered paradigm typically found in processors, we actually define these moves between function units and register files and so on. So for each cycle, an instruction contains these parallel moves, 1 for each bus. So in this case, there would be 4 buses, so 4 parallel moves. And they always tell, let's say, move from this function unit port here to this function unit port here. And because we have these parallel moves, it results in a long instruction word, similar to VLIWs. And as each TTA core is different in its instruction set, basically the instructions will be always of different widths, unless padded to some, let's say, power of 2. And one interesting thing is that the function units can store data in their inputs and outputs. So this basically decreases the pressure on register files compared to VLIWs, for example, where you have to have as many write ports as you have function units that can write at the same time to the register file. But because we can control this on software, we can reduce the pressure to the register files and delay these writes to the register file, for example. Because of this software programmability or control, we can have some interesting TTA-specific optimizations, such as operand sharing, where you keep the same input in your input port of a function unit, and you don't need to move it there all the time. And yes, usually in our experiments and case studies using the same benchmarks, comparing to, for example, traditional RISC processors, we usually get away with a smaller register file with less write ports, which basically translates to less power consumption. And the TTA model is also quite flexible, since, for example, I could add to this core here 20 function units more, and I wouldn't need to do anything else to make it a functioning core. Well, it might not make sense to do that because you only have 4 buses here, so you wouldn't be able to move data between those things. But anyway, it's highly customizable in this sense. Of course, there are some downsides or limitations to this architecture. So, for example, interrupts are quite difficult, but not impossible to do with TTA. Since, for example, the function unit input and output ports are part of the architectural state of the processor core. So you would have to save those on context switches. So we think this is suitable for application-specific processors and accelerators that can run to completion. So now that we have a brief understanding of the TTA, we can look at the TTA-based co-design toolset. So basically, it's our toolset to design these TTA processors, and we've been working on it for nearly 20 years, so the tools are quite robust and tested. And it's also available to download at openasip.org. And we have a graphical processor designer, compiler for C or OpenCL programs, cycle-accurate instruction set simulator, RTL generator, and basically an image generator. So you can basically take a program, design a processor, and you get the output RTL files that you can put on your FPGA or ASIC. It's quite easy to configure, as you can configure the number of function units, what operations they have, register files, how many entries there are, how many ports there are. You can prune the interconnect to have as many buses as you want and as many connections as you want, and different address spaces to instructions and data. In addition, you can have custom operations, which can be used in these C or OpenCL languages, and a platform integrator for example, for different FPGA targets. In addition to these standard features, we basically have this experimental branch where we have SIMD instructions along with their RTL and different optimizations for the instruction stream, such as L1 cache implementations, a loop buffer, and this more exotic structure called instruction register file. So these basically are used to optimize the performance and energy of the instruction stream. And as you can see here, you can design quite small cores. And then again, you can design quite large cores with different numbers of buses. And for example, this one had 16 times 32-bit SIMD instructions, along with scalar operations, of course. So how would the tool flow for TCE look like? So basically, you as a designer have some requirements, let's say for cycle counts or wall clock time or power consumption. And you probably have some kind of a program that you want to run. And then you basically start first by defining a starting architecture in our processor designer. And you can take your program and the starting point architecture and compile it for that architecture. And using the simulator, you can simulate and get different statistics, such as the cycle count. And if you're not happy with it, you can go back to the processor designer and explore the architecture space more. And once again, compile and simulate. And basically, once you're happy with the results, you would then go to the RTL generation phase, where you basically, our tool is able to generate all of the operations in our operation set base, along with these extra things for the instruction stream, for example, and also hardware test benches to initialize your simulations. Also, since we've compiled a program, there is this program image generator that will generate basically an instruction image and data image for you. And these you can basically take into Model Sim or GHDL and get an RTL simulation out of it. And basically these are the files that you could then, with a platform integrator, put onto an FPGA or ASIC as a part of a larger system. So here are two case studies that have been designed with our tools. The first one is called Lord Core, named after an algorithm. So this is basically a software-defined radio coprocessor. And the main thing it does is multiple in, multiple out detection. So basically channel detection in, for example, 5G technologies. So it basically executes these two algorithms called MMSE and LORD. And we've basically implemented them in OpenCL for this processor. And please don't ask me more about these algorithms. I'm not an expert on those. But in this specific core, we basically have two sides separated here. So this upper side is scalar data path, where we have 32-bit values on the buses and between function units. And the lower side is basically a SIMD data path with 16 times 32-bit instructions or vectors. And basically the SIMD is there to get computational performance and exploit this instruction level parallelism. And there is a publication on this. I don't actually have the link here, but well, the conclusion there was that we can provide very high performance compared with accelerators and GPUs while being very energy efficient. And the important note here is that the penalty for programmability with this TTA was very small. So even though it's completely software programmable, you could run basically anything you want in addition to MMSE and LORD. Still, the penalty for that was quite small. So this was kind of a larger core. So on the other end, we would have these LOTTA cores or low power TTA cores, which basically have 3 buses and a scalar data path only. And basically we have a register file, ALU, and a multiplication unit, along with LSU for memory. So there were a few variants in our study, so between 1 and 3 stage pipelines. So basically that means that everything in a typical RISC pipeline is done in 1 or 3 pipeline stages. And the idea here was to target fast execution of control code along with some DSP or signal processing capabilities. And because we have a long instruction word architecture, like I mentioned, we incorporated this instruction register file, which is, you could think of it as a software controlled cache to improve the energy efficiency. And the results, we got up to 2.6 gigahertz clock frequency on this 28 nanometer process technology. And we compared it to a RISC-V processor called Zero RISC-V, which Esko also mentioned earlier. We matched the function units inside the core, and for the core only, we got 2.5x lower energy consumption. And this is largely also due to the very efficient compiler that we have. And of course, the parallel execution. In a design point where we tried to maximize the clock frequency, we got over 2x higher clock frequency and 1.8 times lower wall clock time comparing to the Zero RISC-V. And this was achieved. This also achieved a similar energy delay product. In another design point where we optimized for energy consumption, on average, we would achieve 14% better energy delay product and up to 68% better comparing the Zero RISC-V. So those kind of, we think that they prove that the TTA programming model can be quite effective and energy efficient. So if you would like to learn more about the TTA and our TCE toolset, you can visit our website, for example, and start by doing this tutorial where you have everything from start to finish using our TCE toolset. So this is all I had. Thank you, and make sure you visit our website.
Okay, thank you, Joonas. We have a couple of questions in the questions and answers section. So the first question is how easy or difficult it's to introduce pipeline registers into the TTA communication infrastructure.
Yeah, that's actually a good question. So basically, there are kind of two places where you can put these pipeline registers. So the first place would be in the instruction stream. And this is actually configurable. Currently, it's around from one cycle to 3 cycles, plus some extra cycles if you want. And that is for the instruction stream. But the second part is that we actually do this pipelining inside function units. So basically, you can define, when you define these function units, that but what would be the delay for that? And let's say you have an addition operation. So you would, when you configure the addition, you would say that, okay, this will take 3 clock cycles. And that pipeline of 3 clock cycles for the addition would be what the compiler sees. So I hope this answered the question.
Yeah, is there ever a need to pipeline also the interconnects, or is it unnecessary?
At least we don't really do that, but usually the interconnect hasn't been like the bottleneck. Although it might seem that it would get really messy with all the connections, but usually it's been elsewhere, either in the instruction side or multiplication or something like this.
Yeah, so there are the input and output registers in the function units, so that helps, I think.
Yeah, it kind of isolates the interconnect from the function units.
Okay, then there's another question there. You had in one of the slides, you had the image mentioned. So what do you mean by image in this context?
Right.
I think. Yeah.
Right. So program image. So basically, it means like the binary or whatever you would call it here, like representation of your program. So basically program binaries.
Okay. Thank you. And I think we don't have any more questions now. So thank you, Joonas, and we move forward.
Okay, thank you.
Next we have Hesam Zolfaghari. So are you ready, Hesam?
Yes.
Okay.
So hello everyone, my name is Hesam Zolfaghari, and the title of this presentation is Packet Processing Hardware for Software-Defined Networking. So short biography, I'm a member of Yarin Hurmi's research group at the Electrical Engineering Unit of Tampere University. I work on packet processing architectures. And so far in our research works, we have multiple variants of a programmable packet parser and the packet processing pipeline. The research goals are flexibility, which in this context means protocol independence, so that you can have hardware that can provide functionality for different protocols by means of software without any change in hardware, and also at the same time maintaining performance level, the required level, and keeping the area low. And regarding our own activities, there is some research that is not yet reflected in our current list of applications. So for instance, low complexity implementation of active queue management, and also memory efficient hash conflict resolution. And also currently we have a technology transfer agreement to a Swedish company under Tetramax EU project. So here's an outline. So I start with the required background, and I go forward to present our contributions and finally the conclusion. So packet processing is obviously the processing of network packets. It is performed in switches, routers, network interface cards, firewalls, and intrusion detection systems. And also the operating system's kernel is also involved with it. So it means that also the end nodes or also the source nodes of the packets are involved in packet processing. The main performance criterion is maintaining a high throughput, and also the dominant pattern is match and action. It means that you match on certain fields of the packets, and based on the result of the match, you perform the required actions. These are some of the operations involved in packet processing. So we have parsing, integrity checking, manipulation of header fields, tunneling, state modification, lookups, classification, fragmentation and defragmentation, traffic management, and also other operations. And packet processing is done both in hardware and software, and the performance requirements and the layer at which processing is to be done dictates whether a hardware solution or a software solution or a hybrid solution should be taken. Then we have this important question of why we need custom hardware for this purpose. And the answer is that because of its high throughput nature, and also the fact that the development in line rate in physical layer has surpassed the developments in processor speed. So we need custom hardware. And also, although current general purpose processors are very powerful today, but the performance enhancing techniques they use are not very helpful in packet processing domain. And also it's important to know some of the latest developments in the world of computer networks. So for instance, software-defined networking is an approach to computer networking in which control plane functionality is taken care of by a remote controller, which dictates functionality to the forwarding devices. So the forwarding devices just perform forwarding, and they are under the control of a remote controller. And network function virtualization tries to enhance the utilization of commodity servers by assigning those tasks to those commodity servers, and thereby removing those proprietary middle boxes. And actually, middle boxes are devices that perform some add-on functions other than forwarding, like firewalls and some optimizers. So it is in response to these developments that the OpenFlow protocol, the P4 language, match action packet processing, and also programmable packet processing hardware have appeared. So as the starting point for this research, we took the reconfigurable match tables architecture, RMT architecture that was designed originally by people at Stanford. And so it contains a packet parsing and packet processing subsystems. And it's a quite complex architecture, and today it can be found in commercially available switches. So it has been successful, but we identified a number of shortcomings with this architecture that limits its scalability. So for instance, the fact that the parsers use ternary content addressable memories is one such shortcoming. These devices are very power hungry, and also they occupy a large area on chip. Then next one is that there is no action depth. So after each match operation, there is one round of action, but in most cases you need multiple rounds of action after each match. Then the field referencing mechanisms are limited, especially when it comes to newer protocols such as IP version 6 segment routing, where you have header fields that act as a pointer. Then it strictly uses matching for program control. There is no other mechanism. The crossbars that select match fields and action fields are actually very large. Then there is also a high cost for table combination and also configuration of the pipeline. So in this pipeline, the stages can be configured with respect to each other, and also while considering the dependencies. So starting with our contribution, and so the packet parser, we have a building block for packet parsing, and this is called a header parser because it parses a header within the packet. So as inputs, it gets the starting offset of the header that needs to be parsed, the header ID, which is known for the very first header, and for subsequent headers, this is calculated by the header parsers, and obviously the packet itself. And the outputs are the starting offset of the next header, the header ID of next header, and extracted header fields. So for each of these outputs, there is a functional unit that performs this functionality. And so we construct the packet parser by placing these header parsers in a pipeline of 8 header parsers. The data path width is 64 bytes, which means that at every cycle, it can accept a minimum size Ethernet frame. The operating frequency is 1.19 gigahertz, and so this is sufficient for an 800 gigabit per second link that constantly sends minimum size packets. So for 6.4 terabit per second, we need 8 packet parsers, 8 pipelines. Okay, so you can see the pipeline. So the packet parser is made of 8 header parsers that are arranged in a pipeline. So here's a walkthrough of what happens. So the packet arrives, and also the header ID. The header ID is used as an index into a memory called parse control word. And so this provides the operation code for a field extractor. And also remember that starting offset was another input to the header parser. And we get the header field containing the next header indicator. And we compare it in parallel with all the relevant and valid values of next header. And so we get the ID of the next header. So similarly, we get the header field containing header size. If necessary, we modify its value and we get the header size. And sometimes there is a default header size. We add this with the starting offset, and so we get the starting offset of next header. And now that the boundary, the start and end boundary of the header is known, we can extract the header fields for the processing subsystem. So now let's proceed to the packet processing pipeline. So it was designed with the goals of efficient use of memory resources, both lookup and storage memories, and minimizing crossbars. And so I mean crossbars for match key and action input selectors, flexibility, then avoiding or minimizing recirculation of packets, which is detrimental for throughput and latency, support of advanced protocols, and also assigning a stronger role to software. So again, we have a building block, which is called packet processing stage, and the entire architecture contains 512 such building blocks. Inside each packet processing stage, there are 8 ALUs, each of which requires 2 field extractors. Then we have the search key generator or the match crossbar. We have exactly 1 TCAM instance and 1 hash table. So this is in contrast to the RMT architecture, in which each stage contains multiple ternary and exact match memories that can be combined. So how do we combine the tables in this architecture? So there is no hardware logic for that. So we visit the tables one by one as the packets flow through the pipeline. So if the goal is to make a wider table, part of the search key is presented to each of the visited tables, and the search results are also transferred along with the packet itself. For making deeper tables, the same search key is presented to each of the visited tables. And for making wider and deeper tables, both of these operations are done. Then these building blocks or the packet processing stage together form larger units that we call pipe 16. So the entire architecture is comprised of 32 instances of pipe 16, but it is important to note that not all 16 blocks can form a pipe 16. So there are some constraints, as you can see here. And the reason for this is to have some means to reduce the latency, because we have a pipeline of 512 stages. So it takes 512 cycles until the packet traverses the pipeline. So, and sometimes when you have deep memories, deep lookup tables, you can arrange these together so that some of these pipe 16 instances receive the same input. And so there are some multiplexers on the left-hand side, and the select value for them is provided by what we call pipeline configuration board. And so there are some constraints to this. So we allow groupings that result in the form of a binary tree. So if you see that this is only part of the system, so already it's like a binary tree. And the reason for this choice was that with a binary tree, the resulting architecture will be very simple. Then for program control, there is a 10-bit packet ID, also referred to as a tag or a label. And so first it is assigned by the parser. And so at each stage, it is submitted to a packet ID map table that as output, it provides a 60-bit value, which is the aggregate of the program counter values for the instruction memory of each of the functional units. So each functional unit in each stage has its own independent instruction memory. And a few other words on program control. So how do we achieve custom action depth? Simply by using the same tag across a number of pipeline stages. And this tag actually can be changed depending on the outcome of ALU operations and match results. And so we have no hardware logic for configuring the pipeline for dependencies. The software defines what operations should be assigned to each stage of the pipeline. And also another technique called software-based speculative execution. And simply it means that even when the match result is in progress, you can perform some operations, and later on you decide whether to keep them or discard them. And also, as I mentioned earlier, some of the newer protocols, such as IP version 6 segment routing header, contain header fields that act as a pointer, which points to another header field. And if there is no mechanism for dereferencing pointers, the implementation can be very inefficient in terms of the utilization of memories. So we have one specific opcode for pointer-based read and one for pointer-based write. So when you execute pointer-based read, so after execution, at the output of the ALU, the dereferenced field appears, and also in pointer-based write, the field that the pointer refers to is assigned the value that is desired. And going to implementation details, it was written in VHDL, hardware description language. The operating frequency is 1.19 gigahertz. We use the 28 nanometer standard cell library and the so-called worst case operating conditions. And the EDA tools that we used were Synopsys Design Compiler, Synopsys Primetime, and Mentor Questa for verification. So the parser results, so the total area is 3.6 millimeters squared, or 11 million gates, and comparing this with 5.6 million gates in 640 gigabit per second RMT parser. So the performance increase is tenfold, but the area increase factor is only 2. And the total power is 9.5. And so unfortunately, we cannot directly compare with the power consumption of RMT parser, because the power or any details regarding TCAMs are very hard to find, but I can confidently say that this is way more power efficient, because a single TCAM device alone consumes something like some value close to this. Then here we can see the area breakdown of the components in each stage of the pipeline. So obviously the TCAM consumes a lot of area, and after that the field extractors. But then we analyzed the packet processing programs, and we realized that we can use smaller field extractors without loss of functionality, and thereby we had savings of 37 millimeters squared, which is equivalent to more than 200 TCAMs. And here we have a final comparison of this architecture and RMT and 2 variants of RMT. So with this area savings, we can integrate 184 more TCAMs, which translates to 376,000 more IP version 4 prefixes. So there were a lot of technical details. If interested, please refer to this paper. And in conclusion, I can say that although SDN and NFV have special emphasis on software, it does not mean that custom packet processing hardware is diminishing. In fact, on the other hand, new opportunities are arising. There is a lot of room for innovation, and the main challenges are supporting programmability without loss of performance and limiting the complexity and power dissipation. And with respect to the packet parser, we achieved high performance without using TCAMs. And so those TCAMs that would have otherwise been used can be just moved to the packet processing subsystem where they are really needed. But for parsing, they are not crucial. And for packet processing pipeline, we had a more flexible architecture, although it is simpler in hardware. And also the fact that the role of software is stronger here is more compatible with software-defined everything concepts. And the next step is doing the optimizations for FPGA implementation. So that's it. Thank you for your attention. I'm ready to answer your questions.
Okay, thank you, Hesam. While waiting for the questions from the audience, I can warm up with something. So some time ago, packet processors were popular. So can you compare how this differs from packet processors?
Okay, and I'm sure by that you mean the network processors, because there is a lot of terminology. Yes. So actually, network processors appeared sometime in early 2000s. So let's say 2002, 2003, and at that point they were very popular. But the thing is that network processors are just processors. So I mean, they have a program control unit, but they have some instructions for packet or network processing. And so the problem with them, so there were two problems with them. One of them was the issue of programming them. So some of them required microcode programming, and so that meant that they did not have much chance for long-term success. I mean, sustainable success. And the other one was that because of this nature of them, that they were basically processors, providing guaranteed performance was very difficult. But with these new class of packet processing ASICs like this one, you can provide guaranteed performance. Yes, but actually still some network processors exist.
Okay. Obviously, there are no questions from the audience. So I think we thank Hesam again, and that concludes this session. So thank you for attending, and enjoy the rest of the conference as well if you are interested to follow that. So it will keep running until Friday. So thank you and bye-bye.